Hi, this is a quick video to show you how to calculate work in physics. This is the way I do it. The book does a slightly different way. So I've got an equation here. The work is equal to plus or minus the parallel component of the force multiplied by the magnitude of the displacement. So this S that you see here, this is actually the displacement. And the displacement, previously we used to call that delta R, right? So in chapter 6, they've changed the variable on you. It's going to be S. So here's your displacement. We have four different pictures, A, B, C, D, where you can see different forces act, but in each case, the force magnitude's the same, 100 newtons. The directions are different, right? And the displacement is always the same, 4 meters, same direction. Let's see how we solve part A. So first thing I always do is I just draw a picture. Exactly the way the force looks and the displacement looks, and I put them at the exact same starting point. Then I go ahead and I draw a coordinate system. This is called the parallel axis, and this is the perpendicular axis. And then I'm going to go ahead and look at the components of F. There is F parallel, and there is F perpendicular to S, right? So parallel and perpendicular to S, and the angle here is 30 degrees. Now, when you do a force, when a force does work during the displacement, it's only the parallel component of the force that does work. So we need to calculate this component, and we can completely ignore that component. Let's write down our equation here. So the work, it's equal to plus or minus F parallel times S, okay? And I need to first choose the plus or minus. That asks the question, is F parallel in the direction of S, or is it opposite S? It's in the direction, so I choose the plus. Then I got to calculate F parallel. Look at the F parallel component. It's the adjacent side to 30, so that's the full magnitude F, right? Times adjacent is cosine of 30 degrees. There's F parallel. And then we need to put in the magnitude S. Let's plug in the numbers. So we got a plus 100 newtons cosine 30 degrees times 4 meters, and when I put that into the calculator, this is what I get. 346 newtons times meters. That is the work done in part A by the force during that displacement. As an aside, a newton times a meter, we define that to be equal to a joule. So that's another unit for work, joules. Let's look at part B. Again, start in the same way. Draw the force and the displacement from a common origin. So there's your force. Here's your displacement. And this one is actually kind of easy to do because if you think about it, all of the magnitude is parallel to S already. So when we do the formula, we're just going to say W. Is it plus or minus? Well, F parallel is opposite of S, so we choose the negative sign. And then I'm going to put, for the F parallel, I put the whole magnitude of F there because it's all parallel to S. And then I put the magnitude of S. Plugging this in, we're going to have minus 100 newtons times 4 meters. And we get a work done in this case of minus 400 newton meters. That's part B. Let's look at part C here. Again, start as usual. Draw the force and the displacement from the common origin. So there's your force. There's your displacement. Go ahead and make your coordinate system. Really all we care about is the parallel axis, right? And so all I care about is the part of F that's parallel there. Here's my angle. This is F parallel, and they are in opposite directions, F parallel and S. So we'll write the work as follows. W, I choose the negative sign. F parallel, that's going to be the magnitude of F times the adjacent side, right? of 50 degrees, cosine 50, times the magnitude S. Plugging in our numbers, we'll get our answer here. And in this case, the work done, part C, comes out to minus 257 newtons times meters. All right, let's look at D here. I'm going to carve out some space here to do D. Again, same as before. Draw your force vector from the same spot. Draw your displacement vector. And let's look at the parallel direction to S. Hey, look at that. F is completely perpendicular to S. Guess what the answer for the work is here? Easy one, right? W is equal to 0 because F parallel equals 0. All right, so that's how I calculate work. Now, in this example, we had 4 different cases. Each one had a single force and a displacement. In a lot of problems, you'll have multiple forces on the same object during a single displacement, and you can calculate the work done by each of those 4 separately using the method that you've just seen here.